Okay, this is video 1 for the lifting mechanisms unit. For the learning goals, I want you to understand what a degree of freedom is and how many of them there are. I want you to understand how to reduce shock. I want you to be able to discuss various types of lifting mechanisms and describe what passive assistance is. Right, so in many different situations, competition robotics are required to elevate or reorient game objects. So to do this, we need to have some sort of lifting mechanism. So first off, we need to understand what a degree of freedom is. This is something's ability to move in a single independent direction of motion. So to be able to move in multiple directions means to have multiple degrees of freedom. So for example, moving up and down is 1 degree of freedom. Moving left and right is another. The ability to move up and down and left and right would be 2 degrees of freedom. All in told, there are 6 degrees of freedom. The way I like to think about it is a Cartesian coordinate system. So on a Cartesian coordinate system, you have an x, a y, and a z-axis. So motion along each one of those 3 axes is 1 degree of freedom. So movement along the x-axis, movement along the y, or movement along the z. So as you look at your screen, moving left and right across the screen would be 1. Moving up and down on the screen would be a 2nd. And coming out of or going into your screen would be the 3rd. So that's 3 degrees of freedom. 4, 5, and 6 are rotation. So I can rotate around the z-axis. I can rotate around the x-axis, or I can rotate around the y-axis. That makes, in total, 6 degrees of freedom. And that's really all there are. There is no 7th or 8th. So, at least not to my knowledge. So we have 6 degrees of freedom. So the ones we're going to discuss, basically there are kind of like 3 that we're going to discuss. First is twisting. So this would be like rotational along an x or a y, if you will. So we got twisting. The second is linear. And there's different ways of doing linear. We can have like this elevator platform here, which can move up and down. Or we can have a sliding part on a robotic arm that can slide in and out. So that would be a linear. And then we have rotation about an axis perpendicular to an arm. So this is just like your generic robotic arm, how it moves. It's a rotational one, so it can rotate back and forth. Now, first off, for our lifting, we need to talk about elevators and how we can use these. So an elevator, it uses a linear motion to pick up an object vertically with 1 degree of freedom. So an elevator picks things up and down. So the elevator must convert the rotational motion of the motor into a linear motion of the platform. And there are different ways of doing this. The first way is a rack and pinion. So for a rack and pinion, we have a gear moving along the linear motion racks. And we have torque being applied, so we have the motor applied to the gear, or we can have motor applied to the rack as well. Now this gear has a radius. So when we go to do some calculations here, torque equals a force which is perpendicular to a lever arm distance. The force will be acting on this linear or these linear gears here. So looking at this torque equals this force times the radius of the gear. So the amount of force would equal torque divided by the radius of the gear. If we assume the torque to be constant, so the motor cannot supply any greater torque, notice that as I use bigger gears, as R becomes bigger, I have less force it can apply. So these rack and pinion setups work better with smaller gears. You get the most force using a smaller gear. Now, the way we set these up, we have to use a device called a linear motion rack. That is a device that attaches itself, you can attach the motor and the pinion gear to, and then it kind of wraps around the other gears. You also have to use the sliders. I have those internal and external sliders for my linear, those little rails that the linear motion parts slide in and out of. But that's how you would build a rack and pinion elevator of sorts. And again, if you want the greatest amount of force, to pick up the greater objects, you have to use a smaller gear. Another type is a chain and sprocket type. So here we have a platform attached to some chain. Up here we would have the second half, another sprocket that's able to turn. We would attach the motor to either the top or the bottom sprocket. It would work better if the motor's on the top sprocket. And again, we see that force equals torque divided by radius. So if you use a really large sprocket, you will not have as much force acting on that platform. So again, this is a case for using smaller parts to get greater force. Some problems with this one is that your total height is fixed. If we go back to this elevator right here, this platform can move up and down. And remember that we're limited by 18 inches for the height at the start of the competition. So the nice thing about this rack and pinion elevator is that you can start below 18 inches and then rise above 18 inches. For the chain and sprocket, these two are fixed. So it wouldn't be a very good way. I mean, you start off at 18 inches and you wouldn't get a height of greater than 18 inches. So it's something you'd have to think about when you're designing it. Another type is a winch mechanism. So for this one, we have a motor attached to a pulley, which then has a string that goes down to your platform. So we have our force, torque, distance, which is going to be the radius of this. And once again, we see that force is equal to torque divided by radius. So you need to have a smaller barrel. We usually call these barrels that wrap up the string. Now for these ones, they do look a little limited. What you could do for this one is you could place the motor at the bottom, have the string go up to a pulley, and then come back down and attach it to the bottom of your other bar that you want to slide. So as this motor turns, it wraps up that string. You're pulling down with a force on the string, which then picks up on the other part of the string with the same force. So that'd be one way you could use the pulley system, and that would pick up your elevator style. Another type is a multi-staged lift. In this one, this is kind of a unique design. We have a chain and sprockets, and we could attach the motor at one of these. So as the motor is turned on, what you would do is you would have the force, you'd have this motor pulling down on this chain and then pushing this chain over. So as this pulls down, it's going to pull up on this chain, which pulls down on this part of the chain, which lifts up on this one, pulls that part down, picks that one up. And what that does is it causes this platform to rise. With this design, we've got our linear racks. We've got these sliders at those positions, and it's all one continuous chain, so you don't have to have any excess chain that's slacked over. And for this type of lift, I've tried to build these before. They're very complex and complicated. What ends up happening is that they get too large this way, and there's a lot of scrub, there's a lot of torque inside these ones, a lot of friction, and I just haven't had any luck building one of these. I'm sure there are designs out there that would be better fit for this. The next type is a scissor lift. And in this one, what's nice about these is that you got a minimal retraction height, so it can go underneath field barriers. And then as these work, you got a motor that applies a force. Usually you can use rack and pinion. There's other designs. So this one applies a force in. So as that applies a force in, because we got these fixed points here and here, in order to make up for it, there's a force that lifts up that picks up this entire system. So we get like a bit of a torque, if you will, acting on this. Now these tend to be heavy. You have to, like, if we take a look at this design right down here, I would think this is a bad design because it's using these bars. And those bars are very flimsy. They're very easy to bend. So when you build this, you want to use C-channels or chassis rails, something that's a little better gauged, a little better, a little stronger, but that makes it heavier. These don't deal well with side loads, so they're really easy to push over. You have to build them very precisely. You have to make sure all of your distances work out. And the stability decreases as the height increases. You're moving your center of gravity higher and higher, which makes it very, it really reduces the stability. And then loads very high to raise. So at the beginning of the travel, they're kind of fast and then they slow down as they get taller. When you build these, you have to make sure that there's a sliding component up here and down here. So as you build these, you have to keep the geometry in mind. Alright, so that is some different types of platform elevators. We'll talk about some other ones in the next video.